This is lesson 2-3's homework assignment in the textbook. We are on page 82. So we're looking at number puzzles. So question number 2, where we're starting, we're going to complete the number puzzle at the beginning of this lesson for the individual. So on number 2, someone who is 50 years old. So we are going to start with someone who's 50. And you flip back to the beginning of the lesson. And here is the number puzzle. So we're going to write down the age, which we got is 50. We're going to add 3. So 53. We're going to multiply by 5. So 53 times 5 is 265. Subtract your age. So we're going to take away 50. 215. Add 9. It's 224. Divide by 4. 56. Subtract 6. 50. The number you get is your age. It's what we started with. So our final answer here is 50. And that's what this number puzzle is supposed to do. You plug in your age, and then it is supposed to repeat it out to you. Okay, so question number 3. We flip back here for a second. Question 3 says great-grandfather Odell, who is 97 years old. So we're going to just follow this again with 97. In the end, it should produce the number 97. So we're going to add 3, that's 100. We're going to times by 5, so that's 500. Subtract the age of 97, so that's 403. We're going to add 9, that's 412. We're going to divide by 4, and that's 103. Subtract 6, and we are at 97. Okay, so where we started is where we ended. Based on this number puzzle, that's going to happen every single time. All right, number 4. We slide this over. This one's a little tricky because it's someone who hasn't been born yet. So how do you express their age if they haven't been born yet? So they're expected to be born in half a year. So half a year would be 0.5. So if they were born half a year ago, they would be 0.5. If they were just born, it'd be 0. And so the only way to express someone who hasn't been born yet would be to go into the negatives. So it's going to be a negative 0.5. So negative 0.5. Because in half a year, when we increase it, we add half a year, will be 0 right at the birth. And then if you added another half a year, they'll be half a year old. So negative 0.5 is going to be used to express the baby who's going to be born in half a year. So let's go ahead and run these numbers now with this. So we're going to add 3. So negative 0.5 plus 3. That's going to be 2.5. We're going to multiply by 5. Then we're going to subtract your age. Now, when you subtract the negative, it's like adding. So don't subtract 0.5, subtract negative 0.5. So you're actually adding 0.5, so it's going to be 13. So 12.5 minus negative 0.5 is 13. And then we're going to add 9. We're going to divide by 4. And we're going to subtract 6. And sure enough, we end up at our negative 0.5. Okay, back to number 5. Someone is 192 months old. Now you could convert that to years, but you don't have to. We're just going to run with 192. If you wanted to convert that to years, from months to years, you would divide it by 12 because there's 12 months in a year. But we're just going to run it in terms of months. So we're going to add 3, so 195. We're going to multiply by 5, 975. Subtract your age. So we're going to subtract 192. Add 9. divide by 4, and then subtract 6, and we end up at 192. Okay, so that completes that number puzzle. So 2 through 5 was all just using that same number puzzle. Once you see that it's always going to produce the end, you kind of get the hang of it. So now for number 6 and 7, we're going to go back and complete the 7 is heaven, so that's right here. We're going to go ahead and run that one. And then you're going to pick a number in this given range. So this may have been confusing to you the first time you've seen it, just looking, what does this mean? So we should know that these are less than and greater than symbols. Okay, so what this is saying is x is greater than 250 or x is less than 500. So the range here is between 250 and 500. What does that mean? They just want you to pick a number that's between 250 and 500. So some of you might say, well, why didn't they just say that? Well, we're just getting used to seeing some of this notation here. So this is x greater than 250, x less than 500, something in between. So for instance, 300, 400, or any random number that's between 250 and 500. So I'm going to start with 400. Okay, it says any number in the given range. So 400 is between 250 and 500. That's a good one. And now I'm going to go ahead and run the 7 is heaven puzzle. So I have a 400. I'm going to add 1. That's 401. Multiply by 2. That's 802. Multiply by 3. 2406. Then it says subtract 4. Then I'm going to add 5. And here's where this can get a little confusing. Very last step says subtract 6 times your original number. So first we need to know what is 6 times my original number. So my original number is 400. 6 times that, so times 6, is 2400. So the number I'm subtracting is 2400 because it is 6 times the original number. So I'm minusing 2400 from this. We'll take a look at what I'm going to get is 7, and that's what this number puzzle always does. That's why it's called 7 is heaven. It's always going to give you the number 7. So any number that you choose is going to work there. Okay, looking at number 7 now. This says pick a number between 0 and 1. That's what it's talking about. So think about the numbers between 0 and 1, fractions and decimals. Now, notice it doesn't have the equals to sign on these less than and greater than, so you can't choose 0 and you can't choose 1 because it doesn't say equal to. It says either greater than 0 or less than 1. So it has to be between them. So I'm just going to pick an easy number like 0.5 or a half. Let's go ahead and run this. So if I add 1, that's 1.5. Multiply by 2, I know that that's 3. Multiply by 3, that's 9. Subtract 4, that's 5. Add 5, that's 10. And then subtract 6 times your original number. If you do 6 times 0.5, 0.5 is a half, right? When you multiply by a half, it just gives you half the number. So it says subtract 6 times the original number. 6 times 0.5 is 3. 6 times 0.5, because you're taking half of the number, is 3. So it says subtract 6 times the original number. So subtract 3 from 10. And sure enough, we get number 7 again. 7 is heaven. Okay, question number 8. Will the 7 in heaven puzzle work for negative numbers? Well, off the top of your head, you might not know the answer to that. A couple things you can do. One, you can look at the process that they went through to create this. Okay, you use the algebra to create this. You're taking any number, and you're adding, and you're simplifying and doing all this, and it comes out to 7. So based on the algebra here, I can already see that I can plug in a negative number, and it's still going to simplify to 7. So the answer is yes. But what I would do to test that out, if I wasn't sure, is actually just run this with a negative number. So for number 8, let's run this with something like negative 10. Let's see what happens. So I'm going to add 1, that's negative 9. I'm going to multiply by 2, that's negative 18. Multiply by 3, that's negative 54. I'm going to subtract 4, that's negative 58. I'm going to add 5, that's negative 53. And I'm going to subtract 6 times the original number. Now 6 times the original number is negative 60. And when I subtract a negative, it's like adding. So subtracting a negative goes plus plus. And negative 53 plus 60 is 7. And so if you show your work, that's a good explanation. So when it says explain why or why not, that doesn't always have to be in words. If you show work, show an explanation, you've explained it. Okay, so you can show it that it works for a negative number. And you could also go back, and the answer key spoke on the fact that the algebra proves that any number can be used in this 7 is 7 puzzle. All right, we're going to use this weird number 1 puzzle here. So for letter A, we're starting with 7. So subtract 8, that's negative 1. Add 7, that's 6. Multiply by 6, it's 36. Add 5, 41. Add 4, 45. Divide by 3, that's 15. Subtract 2 times your original number. Original number was 7, so 2 times the original number is 14. So we're going to subtract 14, 2 times the original number, from 15, and you get 1. Your answer should be 1. It's good. Okay, letter B. We're starting with negative 2.9. Okay, we're going to subtract 8. Negative 10.9. Add 7. Negative 3.9. Multiply by 6. Negative 23.4. Add 5. Negative 18.4. Add 4. Negative 14.4. You may notice adding 5 and adding 4, you could just add 9 and that whole stuff right there. And then you're going to divide by 3. Negative 4.8. And now you're going to subtract 2 times your original number. So if I go ahead and multiply negative 2.9 times 2, I get negative 5.8. That's 2 times the original number. I'm going to subtract 2 times the original number. And when I subtract a negative, it goes plus plus. So I'm really doing negative 4.8 plus 5.8. But you can put in minus negative 5.8. Put in all those negatives and just deal with it. And sure enough, you're going to still get 1. So this is the weird number 1 puzzle. We should get 1 every single time. Now, part C. We're going to run this with the variable n. We still should end up with an answer of just 1. The algebra should simplify all the way down to just 1. So we're going to subtract 8. That is n minus 8. That's how you express it, because you can't actually take that away from n and get a single answer. It's just an expression, n minus 8. Now we're going to add 7. So what we're going to do is we're going to take n minus 8 and we're going to add 7 to it. So what happens when I add 7 to it? I can't combine the 7 with the n, but the minus 8 and the plus 7, they do combine. Okay, and that's going to leave you a negative 1. And so I'm left with n minus 1. So basically the negative 8 or the minus 8 combines with the plus 7 or the positive 7. It leaves you a negative 1, which we write as minus 1. Okay, so we've done the add 7 and the subtract 8. Now we're going to multiply by 6. So this whole thing has to get multiplied by 6. Here's the key to this. The whole thing gets multiplied, so I put it in parentheses. Whatever n minus 1 is gets multiplied by 6. So we already worked on our distributive property here. So 6 times n is 6n, and then 6 times negative 1 is negative 6. So when we multiply this, it has to be the whole quantity. You put it in parentheses and use your distributive property. When you're adding, you can put this in parentheses. It's not going to change the outcome here. But when you're adding, you're just combining things, and you're only going to be combining like terms. We'll talk about that more in a second. But whole numbers combine with themselves. They cannot combine with a variable if they don't have a variable on it. So we're at 6n minus 6. We're going to add 5 to that. So when we add 5, it just combines with the number, not the n. So the 6n is going to stay. Negative 6 plus 5 It's negative 1, so I still have a minus 1. Now we're going to add 4 to it. Again, only combines with the minus 1, so that's positive 3, so 6n plus 3. Now we're going to divide by 3. So this whole thing is going to get divided by 3. We've talked about these rules where you can split this up. So this becomes 6n over 3 plus 3 over 3, right? We can split this into two fractions. We've been doing that in some previous lessons. Now, why would we do that here? Why is that helpful? Well, 3 divided by 3 is 1. So instead of having this fraction looking thing, I've got a plus 1. And 6 divided by 3, we're allowed to do that. The n is just going to stay. 6 divided by 3 is 2. So this is 2n plus 1. That's our next part of the sequence here. And last but not least, we are going to subtract 2 times the original number. Original number is n. 2 times the original number is 2n. So I'm subtracting 2n, 2 times the original number. Subtracting 2n from this does not mess with the plus 1. It only is going to interact with a like term. So 2n minus 2n, they will end up canceling out. And what are you left with? 1. And so the algebra, while it's more complicated, holds true to the number puzzle and will give you just a 1 at the end. Okay, number 10. We're going to use the double is trouble. So all of these should end up doubling. So I'm starting with 17. Double 17 is 34. So I should end with a 34 here if this double is trouble puzzle works. Okay, I'm going to subtract 11 from it. That would be 6. Multiply by 3, that's 18. Add 5 times your original number. So first thing I need to find out is what is 5 times my original number. So 17 times 5 is 85. So I'm adding 5 times the original number. So 85 is being added to 18. That's 103. We're going to add 1. It's 104. Going to divide by 4. So 104 divided by 4 is 26. I'm going to add 8. That's 34. Your answer should be twice your original number. Sure enough, times 2, 17 is 34. So this number puzzle is working. Okay, point 4, going to subtract 11. So negative 10.6. We're going to multiply by 3. We're going to add 5 times the original number. So I need to do 5 times 0.4. That's 2. So I'm taking negative 31.8 and I'm adding 5 times the original number, which is 2. So adding 2. Then adding 1. And notice, I'm dealing with negatives. I can do this in my head, but I'm pretty likely, if I'm going too fast, going to make a mistake with my negatives. With positives, just run with the numbers. But negatives, don't be afraid to just plug them in the calculator. Make sure you don't make a silly mistake. Okay, so we did plus 1. Now we have to divide by 4. Then I'm going to add 8. And it should be double my original number. 0.4 times 2 is 0.8. So the number puzzle worked for a decimal. Okay, now we got to run it with n. This is where it can get a little complicated, but this is kind of what it all boils down to. This is the most important part. So we're going to subtract 11 from n. That is n minus 11. Now we're going to multiply by 3. When you do that, you need to use parentheses. So it's 3 times n minus 11. So you're going to distribute here. So it's 3n minus 33. We're going to add 5 times the original number. 5 times n is 5n. So we are adding 5n to this. Adding 5n. When we do that, the 5n cannot combine with the 33, or the negative 33, because they're not like terms. There's a variable. It can only combine with another term with the same exact variable. So these will combine. So I will have 8n, and I still have minus 33. We're going to add 1. Now that doesn't have a variable. It only combines with the minus 33. So that's negative 32, dividing by 4. So when I divide by 4, I want to split this into two pieces. And they will divide nicely by 4. 8 divided by 4 is 2, so that's going to be a 2n. The n tags along. So 8 divided by 4 gives me the 2. The n tags along. And then 32 divided by 4 is 8. It's negative 8, so minus 8. Then I'm going to add 8. So a negative 8 plus a positive 8 is 0. Basically cancels this out, leaving me just 2n. Your answer should be twice your original number. My original number was n. My ending number is 2n. I have proven with algebra that this number puzzle will always work. Okay, next up, real quick talking about like terms a little bit further here, down to number 18. So just pretty much simple yes or no questions here. Determine whether the terms are alike or unlike. So we have 22n and we have 22n squared. Are these like terms? Could we combine them? And the answer here is no. These are unlike. And the reason is they do have the same variable. The coefficients happen to be the same, but that doesn't matter. We're only looking at the variables. They have to have the same power to combine. So I cannot combine an n and an n squared. If I had an 8n and I had a 16n, those are like terms. They can be combined. But this is an n and an n squared. They're different, so they're unlike. Cannot put them together. 19, very similarly. When I look at these, the 5 and the negative, that doesn't matter. Okay, but the d and the d match, but the powers do not match. These are unlike. If I had a 5d squared and I had a negative d squared, these would be like terms. The 5 and the negative, they don't play any role in this decision whether they're like or unlike. You're just looking at the variable with the power. I can combine any coefficient if it's a d squared and a d squared. This would be combining a 5 and a negative 1. These would combine, 5 and negative 1 is a 4d squared. I can put these together because it's the same variable with the same power. They combine, they're like terms. If the powers are different, it doesn't matter about the coefficients ever. And it doesn't matter that the variable is the same. If the powers are different, they are not like terms. So I just want to make sure that is really clear, and that's how come I assign those two numbers there. All right, and then we had 22 and 23. So we're going to go ahead and use the distributive property to simplify it. So that's the first thing we're going to do. We've kind of got two sets of parentheses here to deal with. So we'll run through the algebra of that. But then we're going to check our answer by substituting 5 into both this expression, the original, and our simplified version. If we plug 5 into both of them, we should get the same answer. Okay? If we don't, then we know that our simplifying was incorrect. So we always work from the innermost part of the parentheses first. So I'm going to save this 4 for later. First thing I'm going to do when I simplify here is just distribute this. So I'm going to get a 6x plus 21. All of that's inside parentheses with the 4. So now I'm going to distribute here. So that's 24x plus 84. So there's my simplified version. And I'm going to test this and see if it produces the same answer as this. So let me start here because that's easy. They picked the number for me. They said you have to substitute 5 in. So I'm putting 5 in. I'm going to run those numbers. So 24 times 5 plus 84 gives me 204. So if I've simplified this correctly and this expression is equivalent to this expression, they're the same. It's just simplified, easier to use. That's why we simplify, easier to use. But they should be equivalent, so I should get the same answer. So I'm going to plug into this now. So it's going to be 4 times 3 times 2 times 5 plus 7. So if I work my way from the inside out, this is going to be 10 plus 7 is 17. 3 times 17 is going to be 51. And 4 times 51 is going to be 204. So you got to follow your order of operations. Parentheses first, innermost parentheses. When you're inside those, you still have to do multiplication before addition. So 2 times 5 was 10. Add it to 7 and got 17. Okay. Still got to do all of the inside parentheses first. So I've got 17 times 3 inside parentheses. I do that first. That's 51. Last thing I'm going to do is this outside multiplication, 4 times 51. But take a look. I got 204 for both of them, which means I simplified correctly. These are equivalent. All right, so same thing for 23. Now this one is a little more complicated. Lots of parentheses. So you just work your way out. So first thing I'm going to do is distribute here. So that's 3n minus 12. I'm going to rewrite it so I don't get confused. I still have the 11 outside and I still have the n outside. So next step would be distribute the 11. So 33n minus 11 times 12 is 132. That's going to get multiplied by n. So an n times an n is n squared. So this is 33n squared minus an n times the number, they just combine. So it's 132n. So I believe that this is the correct simplified version of this. But to make sure that that's true, I'm going to go ahead and plug in 5 for both of them. So 33 times 5 squared minus 132 times 5. So order operations, I'm going to square first. So 5 squared is 25. So 25 times 33 is 825. And 132 times 5 is 660. So 825 minus 660 is 165. So I'm going to go ahead and plug 5 back in up here now and make sure I get 165. So 5 goes in for n. I have 11, 3, and then in here, n becomes a 5 minus 4. I've got all these parentheses. Looks a little confusing, but just work your way from the inside out. So 5 minus 4 is 1. 3 times 1 is 3. 11 times 3 is 33. And 5 times 33 equals 165. Now you might look at that and be like, man, I can't keep track of all these parentheses. This is confusing, right? It's complicated. And that's the whole point of this. Why do we simplify? Think about those words, simplify, to make it simpler. If this was some kind of equation that you were working with in the real world, let's say you're part of some manufacturing business, and this formula computes how much money you're going to spend on something. Okay, if I had to run through this every single time I wanted to figure something out, it's a pain, right? We just looked at it, we're like, man, this is complicated to deal with. So we simplify to a much easier expression to use. And so on a daily basis, plugging into this, I can run my numbers real quick. They're equivalent, but simpler. And that is why we simplify.